So, mastering control systems for optimal heat pump performance. Unlike a furnace where, we can kind of set it and forget it, temperature goes down, it comes on, temperature comes up, it goes off. How an air source heat pump operates, and because we have now generally two heating sources. We have the air source heat pump and we have the supplementary heating system. So how those two work with each other can actually have a large impact on the economy of operating an air source heat pump, and also on the greenhouse gases emitted using the air source heat pump. So the current market offering, we're gonna look at what there is in controls for centrally ducted systems and why we should care. We'll look at the methodologies. Before I start, again, we will be staying away from brand names, but I can say with relative impunity that most of the manufacturers of these systems have controls that will do any and or all of these methods. Okay? We'll take a detailed view at the various control approaches. We'll throw this into the case study home and see what the web application spits out in terms of what are the results, in terms of what's more cost effective to run, what is better for the greenhouse gases, et cetera, et cetera. Case study, and then at the end, again, we're telling you what we're going to tell you, then we will tell you, and then we will tell you what we told you. Very much like an essay. We're going to take you back to grade 10 English. You thought, I'm never going to use that again, and then you came here. So, heat pump, electric versus gas backup. And quite honestly, I'm not going to spend an awful lot of time on the electric. It's not as common in Alberta. I think most of what we see will have a hybrid model of having a gas secondary system. And there's a couple of reasons for that. One is, and the most common one is, most homes have gas to the property, and they use gas for other things. In my home, if I went to an air source heat pump, I would still have a gas backup because I want to keep my gas barbecue, and my wife wants to keep her gas fireplace. And there's a gas stove that we may or may not fight over every once in a while. So, but with an electric system, the heat pump runs continuously over its full operating range, and the electrical resistance coil is just there to back it up. So these will run simultaneously, okay? When we get into a natural gas situation, the natural gas will kick in and disconnect the air source heat pump. These two do not run at the same time, okay? So those are the control strategies that we're going to be talking about today.
When it goes in the defrost cycle, it doubles, right?
Yeah, well, you're using the heater to defrost the coil. Yeah.
Sorry.
So control approaches, what's out there? There's many different ways to control a hybrid system, and again, that's what we're sticking with today because that's what's most applicable to the Alberta market. We can use that outside temperature balance point cutoff that we calculated in the last section. We can use a single temperature economic cutoff, okay? So what some of these things will do is you can actually figure out how much your different fuel sources cost, and you can determine a temperature at which point the fuel source switches. And then there's a two-stage time temperature hybrid. And there's a couple of different iterations of this that we'll go over. So why should we care about the selected control approach? Well, because everybody has different concerns, right? For the homeowner, they want to have a low installation cost, low operation cost, and they want comfort. Those are their primary concerns. I will add into that environment because I was called out on that in Canmore 2 days ago. So some people care, some people do care about the environment. Honestly, I think if we're being truthful with ourselves, we would say that the driver for a lot of people that have been buying these things up to this point have been rebates. Okay? For the builder / HVAC contractor, you want to be competitive in your pricing. You want to have a business case for doing this, right? There has to be a reason. We're not doing this for free. We're not doing this for practice. We have to be able to make some money at this in order to continue doing what we do. We have people to pay, rent, all that other good stuff. And we do want customer satisfaction. It really sucks if you go through all that work and then the customer starts bad-mouthing you. I mean, at worst, and we all know this, if somebody's angry, they'll tell everybody. If they're happy, they'll tell one person, right? It's very unequal that way. And then from Natural Resources Canada standpoint, they're worried about the energy management and they're worried about the environment. And they threw this little graphic in here for me to not forget to talk about the greenhouse gases. So let's investigate the different control scenarios for this case study home. So this one here, we're going to cut off the heat pumps at their thermal balance point temperatures. So that's one of them. We're going to operate the heat pump or supplemental heat when it's most economical. And this works in different jurisdictions. We found out yesterday, Medicine Hat actually has time of use data, and at some point in time they might actually charge people electricity based on the time of use. In the province of Alberta, our cost of electricity, although we only pay the contracted rate that we pay, the retailers actually pay different prices at different hours of the day.
Yeah, in peak periods.
Yeah, so there are times in Alberta when electricity is almost free during the year. There are times in Alberta where electricity is over $1 a kilowatt hour. Okay? So when you're sitting there complaining about your 8.88 cents per kilowatt hour rate, think about, you could be paying $1 an hour because that's usually at the peak. $1 a kilowatt hour is usually at the peak times. So we can look at this from an economical standpoint, and then again, the two-stage time temperature-based hybrid approach. So what this one is this is based on how much time we run the air source heat pump for and how successful it can be in bringing heat back into the house. Okay, the control approach one, cut off at the balance point temperature. So that is what we calculated in the first F280 session. So what we're doing is we're cutting it off here at that minus 12.8 degrees. And what we can see from this graph is that the air source heat pump is covering an awful lot of the heating season. Okay, so there's not a lot of time when you're actually running that supplemental. You can see in here a couple of days in January, a few days in February, December, November, and that's kind of normal. So you're covering that, and we talked about it in the last section, that 70% of the heating season is being covered by the air source heat pump. At least. I would think it's a little bit more in this case, just from looking at it. So when we can do that. The other one is a single point economic temperature cutoff. So the COP of the heat pump is lower at colder temperatures. That's the coefficient of performance. So if you're talking about electric resistance heat, that has a COP of 1. It's 100% efficient. And as we get colder, the COP of the air source heat pump can actually, the heat pump itself will work, but your COP is below 1. Okay, so we want to cut it off when it's economical, and it's more economical at a higher temperature where it has COPs of 2 and some of these things in the 3s. So at this one here, we've picked a temperature somewhere around the neighborhood of like 4 degrees Celsius, and you can see it still covers a good chunk of the season, but now your supplementary heating system is kicking in, and this is what runs the most economic way. Okay. So again, if you want to run this in terms of a little bit more running the air source heat pump and saving absolute amounts of energy, it may actually wind up not being as economically feasible as somebody wants. Okay, so again, good, cheap, fast. You can get 2. Same kind of thing with the heat pumps. So control approach 3, a two-stage time temperature hybrid. So in this particular case, your set point, as long as a set point temperature is maintained, of course, nothing comes on. But over the course of time, the temperature goes down in the home. And when it reaches a certain point, the thermostat kicks in and says, hey, we need some heat, calls for heat. So we're going to say this is at 21 degrees, 21.5 degrees Celsius, and the heat pump comes on until that set point is reached. Okay, so that's one possibility. Another possibility is the control approach where it's a time temperature hybrid. So again, nothing's on, the temperature comes down, but in this case, the heat pump comes on in an attempt. On this slide, it says an attempt to bring it back up, but it can't. So this is going to be in your colder temperatures, right? Where this unit just does not have the juice to bring it up to the comfort temperature that we require. So we let it go for a little bit, give it a chance. We have to give it a chance. The building code says we have to. We have to give it a chance to do that. But at a certain point, you know what? You gave it a good shot, but I'm afraid the 100,000 BTU explosion is going to have to go off in the basement and carry this thing the rest of the way. Now, the one thing I do want to call to your attention, and I mean, this graph doesn't really have a whole lot of basis in truth, but what it is I do call people to the attention that when you're looking at the temperature rise over time, okay? So in this slide here, if you look at where the low point is and how long a line it is to get it up, you will find that an air source heat pump takes a little bit longer to heat up a home than what your furnace does. Has a much steeper line, right?
I think that's an understatement. It's a lot longer.
Yeah, well, like I said, it might be a bit of an understatement, but it kind of gets the idea across. It's a much shorter period of time for a furnace to get something to temperature than it is for an air source heat pump. And that's part of the education we have to have with clients, is that we have to warn them that, you know what, when you come in on that minus 20 or 30 degree day and you want to warm up over top of a vent, you may not necessarily be wanting to do that, because what's coming out of that vent is only a few degrees above ambient, and it's coming out with a little bit of a wind chill. So it might actually feel a little bit cooler than ambient, but it is actually heating the home. And I've always equated it, and I equate a lot of things in my life to food. I equate it to cooking beef, all right? A steak you sear because you want that caramelization. A roast you do low and slow. And a house is a roast, okay? Think of a house as a roast. We want to cook or heat a house low and slow if we can. So it's actually a more efficient and more comfortable way to run that. And we'll talk about that in the fourth section.
I'll have to say that is our biggest callback, is that what happens is people set the temperature like 18 degrees at night and 21 in the morning, and their furnace comes on.
Yep.
And right off the bat, depending on the heat pump, if there's a 1.5 degree spread between ask to where's that, it'll just go right to furnace. It says, I can't do that here.
Yeah.
What you call it, like the roast?
Roast versus a steak.
Roast versus steak, yeah.
Yeah.
So
when we're installing these, we can install these with some of these different control systems that will allow the heat pump a little bit longer to work. Okay.
Yeah, so we ask the customer to change their set point in stages, and then the heat pump will come on, and within that 1.5 degree.
Exactly.
These kind of things.
Exactly. So we ask the client to make a few changes to how they operate the home, and that actually drives the point home. That's an excellent example of how, when we're putting this in, we just cannot put this in and walk away. There's a certain amount of education that's required on our part, and again, I will throw my own self under the bus for this. I had my heating device replaced recently. And the guys came in, they did a great job, they replaced it. They were quick, they were in and out, but absolutely nobody came to me and said, okay, so this is how you operate it.
Yeah.
So now, I don't know if they knew that I was in the industry and probably figured out that, this guy might have a clue as to how to operate it, but I kind of think that these guys didn't know me at all. And they were very happy to, take a piece of pizza with them on the way out, as I recall. But they were happy to take that pizza and run out of the house like their hair was on fire. So there's a certain amount of education that we have to provide in addition to that, even if we're replacing furnaces, because it is a little bit different running. If you're going from the old naturally aspirating furnace into a condensing furnace, these things operate differently. The condensing furnace, those old naturally aspirating units, two things about them, good news and bad news. The good news is they never die. The bad news is we really wish they would. All right? They're horribly inefficient. They're generally, yeah, exactly. Yeah, they're just a horrible unit. But a lot of people never figure out that they want to replace them because it still works. So anyway, this one here is the time temperature one. This is kind of the total hybrid approach. The temperature drops, the heat pump comes on, gives it the old college try, and if it can't satisfy it, and this is what you were talking about, we give it a time interval. Okay, in this case, we've given this thing 15 minutes to heat the house. Okay, at this point, it might be that yes, we have too much of a gap to fill, or it might be that it's just too cold outside. Doesn't matter what it is. This thing needs a little help. The supplementary heating system kicks in, and away we go. And this is usually when we're talking about hybrid systems where we want to be. We want to, and actually by code, we have to give the air source heat pump a shot at satisfying the thermostat, if we have one. So this is bringing everything all together. So in 15 minutes, or if it drops to 21 degrees Celsius, we can actually set things to happen, right? So this is what your hybrid approach eventually winds up with. So it's a combination of all the other three approaches together. We've got nothing on, temperature drops, heat pump gives it a good shot, can't quite do it over that 15 minutes, or the temperature drops. It's either or. So if it comes on at 21 degrees Celsius and continues to go down even with the heat pump on, that's an automatic furnace is going to get engaged. All right? Or if it's getting a little bit better, but it's not quite going to make it, we've given it 15 minutes, it's given its good college try, but yeah, our comfort expectation is that we won't be uncomfortable for more than 15 minutes at a time. Kick in the afterburners and let's get this thing done. So again, I talked a little bit about the code. So this is the requirements in the National Building Code. So we actually have to put in controls to prevent the supplementary heater operating when the heat load can be met by the heat pump. Okay, so again, that's that hybridization version. The heat pumps with a programmable thermostat shall be equipped with a setback control that will temporarily suppress the electrical backup or adaptive anticipation in order to prevent the activation. So this again comes in and says, we at least, even if it can't meet it, we still have to give it a chance. Okay, so these are the two restrictions that we have within the building code. So let's look at our case study for a minute. Again, our home characteristics, this is out of the CSA F280. So when we did this, oddly enough, I gave all my information, my HOT 2000 file, plans, all that kind of stuff, and we did a full F280 on this one. And this is what we came up with, heating load and cooling load for the different zones in the home.
Hence the 310.
Hence the 310. All right, so again, we're trying to reduce electricity consumption. We want air conditioning. That was the main driver for most people. We want air conditioning, but there's a rebate, which means that we can get a heating system for the same or a little bit less, right? Like if we go with Don's example, where an AC unit is probably going to cost us $4,000 or $5,000 to install, and the heating unit is going to be $9,000. Well, you're actually getting some of your AC unit paid for if we look at this economically.
Single stage AC is about that 4 to 5.
Yep.
And then a fully modulating.
Yeah.
12, and there's that gap.
Yeah, there's the gap.
The same numbers.
Yeah.
And you get a fully modulating AC/heat.
Yeah. Typically speaking, if you're talking a single stage air conditioning unit, for in that $5,000 range. You're getting a single stage unit, probably with a SEER around 14 and a half at best. 14 to 16. Most cold climate air source heat pumps are operating at SEERs in the 20s.
Yep.
So you're getting a much more efficient air conditioning unit, and you're getting the heating for the same price. Winner, winner, chicken dinner. Where do I sign?
Well, not only that, in modulating ACs, hardly make more noise.
Yeah. So utility pricing and emissions factors. Okay. So electricity and natural gas prices vary. I think we can all agree on that. Some people for electricity, they're on that rate of last resort. Man, I love that terminology. Some people have a contract. Some people have an old contract where they get a really good deal. Some people are on some of the newer contracts where it's not quite as good. So the NRCan sizing and selection app considers the consumption costs. So we actually input the consumption costs, and this thing will actually help us determine an economic scenario, a greenhouse gas scenario. So it'll help us with some of those decision-making parameters. In Edmonton, for our purposes, we assumed a combined rate of 17 cents a kilowatt hour. So that's including our standby charges. Oddly enough, this came out of my house when we were doing. Well, what I did was I took my entire consumption from last year, divided it by my entire bill from last year, less the GST, and that's where we wound up. Okay? Very unscientific. Just so there is no averaging, there's no statistics involved in here. This is a single point statistic. Okay, so that number may vary, but for the purposes of our discussion, this is what we were using. Okay, and 37 cents per cubic meter for gas. I asked him to change this to a gigajoule, but he didn't. Works out to around, I think we worked it out to around it was around $7 a gigajoule, which also includes your standby charges and everything else. And again, that came out of my house. Again, single point in time, okay? The web application currently assumes an electrical grid emission intensity of 790 grams per kilowatt hour based on old estimates. Now, before anybody gets upset about it, we are a lot better than this by a factor of half, okay? And we actually have some slides to demonstrate that. So anybody that was going to get upset about it, and actually I think the only person that got upset was me when I saw this slide, because that's horribly inaccurate. We are way better than this. But when we use this and we throw this into the tool as it sits today, we wind up, when we're looking at energy, purely energy performance, okay? What is going to use the least possible amount of energy? Do we call it the thermal cutoff, the economic cutoff, or the hybrid method? So if we look at those, clearly in terms of energy, the hybrid method wins, okay? So that's your best energy performer. The economic cutoff, when we run the economic cutoff on strictly economics, we don't even run an air source heat pump. Reason being is when we calculate everything into the same dollar figure per heating unit, okay, electricity comes in somewhere around $35, $40 a gigajoule. And natural gas comes in around 7, all in.
Is that based on particular heating degree days?
No, that's just overall.
Just overall.
Yeah, and again, very unscientific for this particular demonstration. This is my house.
That would be heating degree days for Edmonton.
Yeah.
In this case study home.
Yeah, in this case study home, this is heating degree days in Edmonton. Not a big difference to Calgary.
So there's no savings on money, it's savings on CO2.
Well, we haven't gone there yet.
Sorry.
You're getting ahead of me.
Sorry.
I mean, in some sense, you're setting me up. In other sense, you should be up here doing the presentation.
I'm just
So,
looking at the,
yeah. So when we look,
should I do it type of thing if I'm a customer?
yeah. Well, we're going to talk about that too. Okay. So the best energy performer is clearly our hybrid model, but it's really close when we just use the thermal cutoff. Okay. We can still cover a lot more of that time. When we look at cost performance, the winner is never, ever, ever turning on the air source heat pump. Okay? So here's the economics of it today. Okay? And this is, and you know, I've had many people, our company policy when the Greener Homes grant was out was we did not recommend air source heat pumps unless they had a discussion with us. And we would have this conversation with them. Yes, you are going to save energy. No, you are not going to save money. Okay? Today. All right? At some point in time during the lifetime of the product, is there a chance you'll probably start saving money? Yep. There's also a chance you won't. We can't predict the cost of utilities moving forward. But as you can see here, if we took this strictly on face value, we have an existing high efficiency furnace and we want to add an air source heat pump. We are going to spend an extra over and above, and we're not going to take rebates into the consideration here. We're going to spend an extra $6,000 getting that air source heat pump in. So we're spending more money for the equipment for the privilege of spending between $500 and $700 a year more for our utility costs. Okay, we have somebody back here who'll take two. Do I hear three? Do I hear three? But yeah, so economically there isn't a good story here, but that is just a snapshot of today.
I think there's something missing. Like you look at the solar industry, how they got the CO2. If there's supposedly CO2 credits, I think that's missing in this whole heat pump.
Yeah. Yeah, no, you're absolutely right. There's a and like I mentioned at the beginning, this is part of the conversation. This is not the only part of the conversation. When we get into greenhouse gas performance, this was a surprise to pretty much nobody. Our electrical grid is, you know, has some challenges in terms of greenhouse gas emissions. Now, having said that, this is coming out of the software, okay? The 727, the 526, and the 786, that comes out of the software, and as I said before, this is assuming 790 grams per kilowatt hour of generation. We do have something substantially lower than that. So if we're looking at the advantages of each approach, the yellow is where we would caution, where we have exposure to risk. The green is where we actually have some success. So if the homeowner's goals were resiliency to changing energy cost, the economic approach wins. All right, they're looking strictly on economy. Reduced reliance on fossil fuels, because of Alberta's grid and our gas infrastructure, all of these approaches have exposure to that risk. Reduced energy use, you are going to use in absolute terms more energy. But again, you will pay more money for using less energy, which seems like a really good deal to me. But you do get the reduced energy use, which may work for some people's goals. Now, as we heard before, one of the pieces that are missing in the conversation is solar, okay? One of the things that we did with this program, when people would call us, is because we wouldn't recommend, we would get calls, you didn't recommend an air source heat pump. No, not until we have this conversation. And then I'm happy to change it for you if after this conversation you deem it's worthy, right? And Joel back us up on this. He was one of our EAs for a couple of years. He wasn't allowed to recommend them either. But once we give them the information, the next part to that information was offering them how solar could offset it. And it is an absolutely dynamite 1-2 punch, okay? We don't have rebates for it anymore, but we do have the Clean Energy Improvement Program where people can get low interest loans to put those in. You also have the Greener Homes loan from the province and the feds and CMHC. That's a 0% interest loan up to $40,000. So for 10 years. So you can actually get some really good financing options, do that 1-2 punch, and you can offset virtually all those greenhouse gases. You can take that economic solution and just take it right to the end. So it's entirely possible, particularly on a newer home where it's a little bit more efficient. The building envelope's a little bit tighter, so you can have smaller equipment, smaller initial costs, and smaller amounts of fuel used that you have to offset. You can offset that with some solar relatively easily, and you have a really good story to tell. Basically, you're heating your house for free. It's not a bad way to go.
No.
Nope, no, it doesn't matter if the sun's shining or not. Because what you do is you bank your extra kilowatt hours and use them later. And with solar clubs and some of these other ways of operating, I have people that live in net zero or near net zero homes that actually make money on their solar every year. So, and not only do they make money, but it also covers off all their distribution charges. It's fantastic if you learn how to do it.
Is there any carbon trading / credits like the solar?
Yes,
There is.
yes. If you have a large enough solar array, many of the utilities that are on the solar club in the province of Alberta will offer, in addition to the refund on your utility usage, they do have programs where they can offer some carbon credits.
No, I'm talking, that's on solar.
Yep.
But if you do.
No, there's nothing. There's not. There's
Exploring if it's. Or not.
well, the thing about solar, the reason that they do it with solar is that's something we can measure. It goes through a meter, right?
Got it.
It goes through a meter. We know exactly how much we used. We know exactly how much we sent back, and that's measurable. The savings on this is very much a homeowner operation dependent, right? I saw a question at the back.
I was going to say, we've done kind of similar modeling with how adding solar would impact some balance point, set point with the control.
Oh, so the question is, have we done any modeling to see if solar affects the balance point? Those are two totally separate systems. Solar has absolutely no bearing on how the mechanical operates, has no bearing on the efficiency of the home other than offsetting electrical usage. It doesn't improve your insulation, doesn't improve your windows. It just improves the amount of energy you use at the end of the day. Yes, over here.
When we bring natural gas into a high efficient furnace, we convert heat at about 97%, right?
Yes.
So Alberta's grid is 85% natural gas, roughly.
Sure.
On average during the year.
Yep.
The best cogen generators, I'm told by engineers, is about 60% efficient.
And that's if you're using both the generation and the heat. That's provided you can actually use the heat. In a lot of cases, you can't.
A lot or less.
Yep.
But the best one is about 60%.
Correct.
So tell me how we're saving money looking from 30,000 feet on our emissions if we're generating power at 60-some%, and then we got line loss in your transmission.
I was waiting for that part. Yep.
So there's all that loss in our grid and are getting electricity into the home. Where are we saving anything?
Well, I think we've seen up to this point we're not.
COP.
Yeah. So where we do save, okay, where the opportunity is for this is in the coefficient of performance. So it's how many heating inputs we have versus how many heating inputs are we getting. So with an air source heat pump, over the course of a heating season, it probably averages out, 1.5, 1.6 perhaps. Maybe a little bit better for some of the better cold climate guys. The warmer the winter is, the more efficient it is overall. So we do make up a lot of ground there. But as we saw, in terms of grid, you're absolutely correct. We have a grid that at best, the cogen gives us 60%. More often than not, the engine itself in terms of generating energy is physically limited to somewhere around 30. So unless we use that other 30% of heat, we have a use for it, we're actually generating closer to 30%. And then we have 30% of line loss from that, getting it from the generating station to the outlet. So it is an inefficient system, but as I mentioned, we have a coefficient of performance which actually does help a little bit. And again, if we go to the solar, where we're generating it right on the roof, right? You have no line loss between the roof and your plug. So in that sense, it does help offset a lot of those. And that's kind of the point I'm trying to make on this, is that if we look at everything, no matter what it is in terms of sustainability, energy efficiency, whatever it is, if we look at anything just in its own little vacuum, we're lost. Because solar by itself is not an answer. Insulation by itself is not an answer. This by itself is not an answer. Which is why, in our training, we are taught to think of the house as a system, right? It's a series of systems. But what we have to do is we have to look at everything as a system and how everything relates. So I've built a number of net zero homes in my lifetime. That was my job with the last builder I was working for. And we developed a formula for net zero homes. It's very formulaic, it's very easy, it's a highly guarded secret, but I'm going to share it with all of you today. Okay, this is the secret, not so secret formula for creating net zero cost effectively. Step 1, figure out what your cost of solar is per kilowatt hour generated. Okay, that is your most expensive thing, and that's our last resort in terms of building these homes. The next thing we do is we insulate the building envelope, and we tighten the building envelope, and we improve our windows until our cost per kilowatt of energy saved is equal to or slightly less than what our cost per generation is. The next thing we do is we do the same thing with mechanical and recovery systems. So that's your air source heat pumps, ground source heat pumps, drain water heat recovery units, energy recovery units, whatever your pleasure is. We get as good equipment as we possibly can up to a point. And then the last thing we do is generate. Okay? That is the whole equation. And there's a lot of little steps in between there that we have to make sure we get right, but that is the general thinking. So mechanicals are kind of a second step as we're going towards a low carbon society, right? They have a role to play, absolutely, but throwing an air source heat pump, or even a ground source heat pump for that matter, into a 1950s home that's had absolutely no improvements is folly. It's a waste of money.
Well, your cost to do that, because some of those homes had 150,000 BTU.
Oh yeah, no, the wind whistles through those things, on a cold winter's day. I lived in Kamloops for a while when I was a kid, and we rented this one house, so this would have been built in 1977. We had a current of cold air that ran across the main floor of the house about this high throughout the whole year, or like throughout the whole winter. It was crazy. So yeah, we had the wind whistling through. It would make absolutely no sense without making other improvements to throw this at it. But, it may sound like I'm kind of down on this a little bit, and this may show that I might be a little bit down on this, but I'm not. It is absolutely critical as we move towards, high efficiency that we employ some of these technologies. Okay, but they have to be done in conjunction with other things.
Yeah, I would agree with that for sure.
Okay, so a note on greenhouse gas performance. This is after Joe and I kind of lost our minds when NRCan said, "Oh, it's 0.79 kilograms per kilowatt." So they actually did a little bit more research, and they're projected to drop to 390. Truth is, this is also based on, they weren't thinking we were going to shut down our coal-fired plants until 2025, 2026. We shut down our last coal-fired plant in Alberta last year. So we are actually, the good news for Alberta is we are ahead of the grid, or ahead of the curve so much that these guys can't even keep up with it. So we're doing really good things here. We are not near as bad as people make us out to be. Okay? So when we do this, it's very interesting how this all works out, because if we bring this down on a greenhouse gas standpoint to 390 grams per CO2 equivalent, all of a sudden your heat pumps in terms of greenhouse gas emissions become on par with just running natural gas. Okay? Now, as our grid improves, and it is set to improve over the course of the next number of years, the two on the outside there, they get better. So there is a good news story here if we're using the proper data. So what contributes to comfort? Continuous air circulation. Again, we are cooking a roast, we are not cooking a steak. Variable capacity allows us to cook the roast. And thermostat setup, that is absolutely key. We talked about that in the controls. And homeowner education. We can do the best job in the world. We can put in the best products in the world. And if we have a homeowner that is not engaged or doesn't know how to operate it, we are all done. There is no hope for us, because that homeowner is going to be calling us on the regular for some kind of thing. Like we were talking about earlier, you know, I don't have any heat coming out of my register. Well, you do, it's just not the heat you're used to, right? So it's very important. Yeah, it's very important that we have the homeowner education. So what have we learned? Current market offering in controls and why we should care. So we've talked about the different approaches. Detailed review of those approaches. And I think we've kind of, we have a little, he's got a Slido poll on which one you like. And we looked at the case study, the different impacts in that Edmonton home. So at this point, I will entertain any questions people have, if we have any. We've kind of been doing good as we go along, so I appreciate that.
I got one, just like a little comment. The guy was asking in the back there about how solar, you know, doesn't affect, or you mentioned it doesn't really affect too much, but I guess one of the challenges I have is like going in and talking to folks and knowing their plan. They got to be a project manager on what they're doing.
Mm-hmm.
It's a challenge. And then it's like, what should I set my balance point temperature? Well, I don't know how much solar you're putting on. Like, there's all these silos, right?
Yep.
So we got to kind of be a detective. And then it would be really handy if there was a type of mechanism that would be like, okay, you're producing throughout the summer, right? You got this big arc of solar
Yep.
production. Some people won't be able to meet their current demand and the heat pump demand, right? Everybody's different. Everybody has a hot tub or whatever, right? So
Yep.
sometimes you're going to run out of your offset. Yes.
Yep.
So there's
A lot of people do run out of their offset.
even earlier.
You know,
right?
well, usually not, well, it depends on the size of the system.
Yeah.
In my experience, people running out of offsets in net zero homes usually takes into March,
Yeah.
depending on how they operate the home. But on smaller systems, absolutely, you can run out of your offsets in December.
Yeah. Yeah. And it's
Yep.
just so many different, you know, and as a contractor, it's like, I have no idea how
Yeah.
I should set this thing.
So when I'm looking at that, when we're looking at a thermal balance point setting, again, the F280 will help you do that.
Yeah.
It'll identify that for you. That's probably where, you know, if that's the control that you want to use,
Yeah.
I would use the F280 to calculate that for me, and not leave it up to a homeowner or somebody in the field. I would want to have it properly calculated.
Well, but each year you produce a little different.
Yeah, but your production doesn't really matter, because your production is going out, your excess is going out to the grid to be stored later.
Right.
All right. So when you're using it, because you're not just using, let's say you have a 7 kilowatt system up on your roof.
Yep.
Okay. Produces in Calgary, it'll produce roughly 8,400 kilowatt hours a year, which will cover an awful lot of heating load. It may not cover all of it, depends on the size and style of home that they have. But even with that, even if it's covering all the heating load, it's also going to, at the same time, it's covering some of the normal base electrical loads. In Canada, the average base electrical load is about 23.6 gigajoules, or 77, almost 7,800 kilowatt hours is the average for a home. Mine's a little bigger. Because it's gotten a lot better since the kids moved out. If I'm being honest, all of a sudden, you know, my wife and I we know how to operate that little thing on the wall. What do you call them? Switch. You know, we know how to operate it. We don't have, 6 computers running all the time anymore. We don't have all these other things going. My utilities got a lot better being an empty nester. But yeah, so you're also offsetting so some of that, when you're calculating it, has to be in offsetting your electrical base loads, right? So even though they're running out, they may not have run out of the amount of headroom they have simply for the heating requirement, but their base loads may have just eaten up the rest of it for them.
Right. You got to kind of put it
Yeah,
in the same bucket.
yeah. So at the end of the day, they're still on the
Isn't
heat
there
loss.
some discrepancy on these models? Like, there's no way you can know what insulation value is in the wall without opening up the wall. Like, there's some discrepancies on these models. There has to be, because like, some of these models that I use, I go there, like we did a model and it was like 3-story, super leaky house. And I was like, this heat pump is not gonna run. Like, the furnace went down, its gas valve went down, and it's just at a blower motor. And this 3-ton heat pump has been running this whole year and just keeping that place cooking hot.
Wow.
It's an 80,000 F280. It's like, what the hell's going on here?
Yeah.
So it's just like, there's gotta be, it'd be cool if there was a real world way to just like tell the homeowner, hey, you're out, you're done, your production's out, and just like, it's up to you if you want to save energy or save the environment or save carbon.
Yeah.
Like, you're gonna spend more money.
I think what the questions are getting at is less about the balance point and more about how we give homeowners guidance on the control strategy they use. And I think you're gonna cover that in the app.
At the app presentation,
Right,
yeah.
but, yeah, I just see like, okay, yeah, I'll leave it.
Okay. Well, if we don't, we can take this discussion offline if the section 4 doesn't add that, doesn't answer that for you.